All right, so today we're talking about the standard deviation of a random variable. So as a reminder, we define the mean of a random variable x. We also can define that as the expected value, and that is equal to the sum of all of the numerical outputs times their probabilities. Okay, so that's from yesterday. We noted that this is the same thing as saying, x1 p of x1 plus x2 p of x2 plus dot dot dot. The standard deviation, which we use sigma of a random variable, we can also call that, we might say SD of x, the standard deviation of x, just the two different notations you will see. Mostly we'll use the sigma and mu notations, but I want to make sure you understand, is equal to the summation, and this form is a little bit trickier. It's the summation of parentheses x minus the mean of x, close parentheses squared, or sorry, and actually I just want to put the mean, x minus mu times p of x. Oh, and I forgot the square root. The square root of all that. So this is the formula we're going to use. Now, please note the following, that you will use the expected value calculated from mu of x equals the summation of x p of x. So you will use that answer within all of your other problems. Now, conceptually, the standard deviation of x conceptually is a measure of variability. How, and so as a reminder, it is reasonable to get results within 2 to 3 standard deviations. All right. As we defined earlier, so results more than 3 standard deviations from the mean are always considered unusual. 2 to 3 is typically, but we will define at 3. So I mentioned this before when we were talking about the normal model, and we were talking about the idea of unusual. And the idea there is that you get a result, and it's like, I expect to win $20. All right, the game told me I should win $20 on average. Okay, you won only $5. Is that unusual? All right, well, we can look at how many standard deviations. It's not just like, well, 5 is $15 away from 20, so that means this game was rigged. It's a lie. No, we got to ask ourselves, is $5, how many standard deviations away, like z-scores, is 5 from 20? Now, we're not going to answer that question tonight. We're going to kind of get into those questions on Monday. I think that's going to be my focus. But I just wanted to reiterate and get that idea of what we are calculating, what it is that we're trying to measure. For today's work, all you're going to be doing is, the same two things you had to do yesterday, expected value and potentially making a probability model. And then the new part is just calculating the standard deviation. So those are the only things that you will actually be doing. You're not going to have to interpret anything right now. We'll get into the interpretation as we go on. But we want to just make sure in today's work that you're able to calculate as requires. So let's do an example. Hopefully today's not too long. We're going to do the same exact problem from yesterday where we have the probability model and we're talking about gambling or from a game or we're playing and the game was -1, 2, 8, 16. Negative. Thank you for giving me the heads up. 0.8, 0.15, 0.04, and 0.01. And part A was to find the expected value of x. So the mean, which is the expected value of x, was equal to negative, and actually let me just do that in a different color. The mean, which is expected value of x, is what we're calculating, is -1 times 0.8 plus 2 times 0.15 plus 8 times 0.04 plus 6 times 0.01, which gave me what? What did it give me? Someone can go real quickly back to yesterday's notes. This is the same problem from yesterday. What did I get? I thought I got like positive 0.02 or negative 0.02. I can't remember. So asking anybody to look to yesterday's notes. What did we get? Oh, it's going to be a long class if this is the response from.
It was negative, Mr. G.
Okay. Right there. You just got to be able to look to your notes. Not even asking you to make a calculation, just to look at your notes from this example. All right, and B. Find the standard deviation. All right, so first off, remember, the formula for the mean is, the summation of x p of x. That's how I do it. And the standard deviation is the square root of the summation of x minus the mean squared times p of x. And we're going to see how this formula actually works. And basically that's the only new thing that you're doing. It's just you're given this formula. All right, they give it to you on the exam, no matter if it's going to be open notes or not. These are given to you. And so you're just going to be able to plug in this information that we found in the problem in part A and plug it in. So I get the standard deviation. You want to put the standard deviation x like that, you can do that as well. Is equal to the square root, or you can save the square root for later. And we're going to take every x value, We're going to subtract the mean. So what's my first x value? What's my first numerical output? It doesn't get easier than this. What is the first x value?
-1.
-1. Minus the mean that we found. So what's the mean? I'm not asking anybody to do any calculations here. This is like a simple question. What is the mean?
The average.
No, what is it? What is it? What is the value of the mean in this problem that we just calculated in part A?
-0.00.
-0.02. Now this one's a little bit weird because we have a negative, and so you can think of it as plus 0.02. If you want to do that when you're writing your work, please do. For the notes purposes, I'm not. And we just go down the line, and we're going to multiply this by its probability, which is 0.8. You're just picking and placing. This is as algorithmic as things can do. Oh, there's that number, I put that number there. Oh, there's that number, I put that number there. Okay, and that number goes there, and that number, that's all you're doing here. Plus, and we repeat the process. Now, every single one of them is going to be minus -0.02 squared. They're all going to be like that. So the next output is 2. So it's 2 minus that. And I'm going to multiply that by its probability.
0.15.
Plus the next output.
8.
Subtract the mean, -0.02. And I'm going to square that. Multiply by
0.04.
0.04. Plus the next output. 15 minus -0.02 squared. Oh, oops, put the square in the wrong spot. Times its probability.
0.01.
And that's the work. Now, I will be showing you how to do this calculation utilizing the calculator, but you have to actually show your work. So today's homework assignment is very important. So on Monday, I'm going to show you how to utilize technology to do this, to do these calculations. You're like, what did I miss a parentheses? And where do I put the square root? You're going to let the calculator do that on Monday. So in Monday's lesson, I'm going to show you how to let the calculator do the work for you. But you still have to show the formula steps for at least 2 of them. So that's kind of the requirement. You can't just say, here's the answer. We got to make sure. Now, in looking in this problem, I know my average is negative 0.02. What seems like a reasonable answer for my answer or for my problem? What do you think? Before we actually do any of the work, my answers vary from -1 to 16. And so that's like 17 apart. So my answer, if I had to take a guess, I would say something probably, I would divide that by 2 at least, and that gives me 8. So 8 would kind of be an a very high upper value. So if I had to just peg a number, I'd probably be something around 5, something less than half at least in this problem. It's probably even smaller because there's so many answers by -1. All of the answers are right by -1. So I get a bunch of -1, -1, -1, -1, and then a some 2s, a little bit of 8s, and a little bit of 16s. So they're probably, the answer is actually going to even be smaller than 5, if not like 3 or 2. And how I did that conceptually is I know the answer can't be more than 17 because 17 is the range. My standard deviation has got to be less than the range. And I want to think it's a measure of how, on average, how spread apart those values are. The most something is spread from the mean of negative 0.02 is that 16. So yeah, the answer could be really high, up to 16. But since all of the answers are really close to -1, and the mean is negative 0.02, -1 is only about 1 away. So a standard deviation of like 1 or 2 or something around even 1 or 2 is going to be a right answer. That's how you can think about it if you understand standard deviation conceptually. So what I can clean this up, and what I'm trying to say is this is -1 plus 0.02 squared times 0.8 plus 2 plus 0.02 squared times 0.15 plus 8 plus, and now the reason why it's plus is because it's minus a negative. And this, I'm just doing this one because it's going to help me write in on my paper plus 16 plus 0.02 times 0.01. I'm requiring you to do it the long way and type in all of them just for tonight, just to get you some good practice. All right, so we're in our calculator, and I just got to do it all. All right, I like to do the square root at the end just to make, I just like to do square root of my answer at the end just so that it doesn't get me all jumbled up about parentheses. So I just do my inside first. So it was parentheses -1 plus 0.02 close parentheses squared times 0.8 close parentheses. I just got to type it in. Plus parentheses 2 plus 0.02 close parentheses squared times, or I can just put, once I just keep the process going, times 0.15 plus close parentheses 8 plus 0.02 close parentheses squared times 0.04 close parentheses plus parentheses 16 plus 0.02 close parentheses squared times 0.01 close parentheses, enter. Now I'm going to take the square root, shift square root of my answer. So my answer is not 6. It's the square root of 6. 2.5, hey, right around what I said. So 2.51. I hadn't done this problem yet, okay? So I had made up new numbers for you guys when we were doing it. So 2.5, 2.51. And that's all you're doing. You're not doing anything else. But I do want to show you a different type of probability model problem. I do want to show you a new type of example problem where we're going to have to actually do it. So so in this one, I don't want to type it all. Guess I'm going to have to because I don't have it at the ready. All right. So here's the example. It's from the textbook. a man buys a racehorse for $20,000 and enters the horse into 2 races. If the horse wins one of the races, he can sell the horse for $50,000. If the horse wins both races, can sell for $100,000. If horse loses both, then can only sell for $10,000. And he will sell the horse, all right? The chance the horse wins the first race is 20% and 30% for the other races independent. All right, so that's the problem. Let you have a little bit of time to copy that down. So what we have here is a problem like the problems before where we have like a tree diagram or a two-way table. All right, so this problem kind of requires us to do things. So we have the first race where they can win and lose the first race. And the probabilities are 0.2 that he wins and 0.8 that he loses. Then you can win or lose the second race. So win first one, lose first one, win second, lose second. You can win second, lose second. And the chances here are 0.3 and 0.7. 0.3 and 0.7. So remember when we calculate the probability of winning, we multiply. So the chance that he wins both races would be 0.2 times 0.3, which is 0.06. The chance he loses both races would be 0.8 times 0.7, which is 0.56. And, well, you can do the other ones, but you can realize that the sum of these two, the sum of them have to add up, and that gives me 0.62, which means 0.48 for the other ones. All right. If I want to do it, I get a 0.14 and I get 0.24, which together give me 0.38, like I said. So this is that he, both wins, both loss, and this is wins one of them. So I could turn it into a table, but I'm just trying to figure out the probabilities from it, and this tree diagram helps me do that. So x and p of x. So the idea here is that I can win both one win or both losses. All right, we're talking about here we want to actually talk about profit here. We're looking about profit. So what is the profit from winning both races? He can sell the horse for $100,000, but it cost him $20,000 to buy the horse. So what is the profit from winning both? Profit, the difference, right? He can sell the horse for $100,000, if he wins both of them, but it cost him $20,000 to play, to buy the horse. So what is his profit? How much would he make in the end? If he paid $20,000 and he sells it for $100,000, how much does he make? $80,000. Thank you. If he wins one, he can sell the horse for $50,000, but it cost him $20,000. What's his profit? Simple question. He can sell the horse for $50,000 and it cost him $20,000. What's his profit?
30,000.
30,000. He loses both. He's going to sell the horse for 10,000 and it cost him 20,000. What's the profit?
0.
It's close. Well, we call it negative, so it's negative 10,000. And now we also have our probabilities now. So we have our probabilities. This was 0.06 that he wins both, nice and easy. 0.56 that he lost both, that was easy. The other one gets a little bit trickier because you have to know that you can win the first, lose the second, or lose the second, wins the first. But we ended up getting 0.38. They add up to 1, so we know we've done it right. So question A, what is the expected profit? So X, and so we define X as profit. So the mean would equal, the summation of X, P of X, which is for my formula, which is 80,000 times 0.06 plus, I just go right down the line, plus 30,000 times 0.38 minus, because it's a negative, 10,000 times 0.56. So 80, 1, 2, 3, times 0.06 plus 30, 1, 2, 3, times 0.38 plus, oops, I said minus, it's a minus, 10,000 times 0.56. And I get 10,060. So I get 10,000, or it was at 60 or 600? It was 600. $10,600. So should he buy the horse? So if he is correct, first off, let's answer that question. Should he buy the horse and enter him into the races? Yes or no? Should he buy the horse and enter him into these races? Should he buy the horse and do this? Yes or no? Can you hear me? Yes. Okay. Yes. The answer is yes. He should do this. And this is how rich people get rich. This is how people start making money. If they know they have a profit to be made, that's unexpected. Now, they may lose. You might get a horse, oh, the horse lost. And you try to do it again. Oh, the horse lost. Well, now you're in for $40,000. Well, actually $20,000 because you made 20 back. Okay, I'm going to do it again. And so the thing that sets a lot of people differ from other ones is rich people basically have an unlimited number of times that they can play these games. Other individuals don't have the what we call the bankroll to make these plays. If you just stick to the statistics, and if your calculations are correct about the probabilities of winning and losing, then in this case he should play this game and play it all the time. And this is what people find. Some people will find out this information and they've done their research and they've made these calculations, and based on what they've found, while they're going to pay $20,000 for this horse, they're going to make $10,600 on average. But there's variability, and we need to understand that. This is only a smart play if you keep playing it over and over and over, and you're okay with some of what's called the swings of losses. You're playing this in the long run. This is why poker is seen by many individuals as not gambling, because it's really a probability. It's really an expected value game. If you know that you should do this a certain way or make this call or make this bet because on average you're going to win money, then you do it every time. Even though something bad happens and you lose, it means that you made the right decision. And if you keep making the right decisions over and over and over and over, if you keep playing it, these expected values will eventually turn around. B, find the standard deviation of profit. All right. So standard deviation is equal to the summation of the square root of x minus the mean squared times p of x. All right. So we're just going to take our same outputs. So, and I'll do the square root afterwards. So it's 8,000 parentheses 80,000, sorry, minus 10,600 squared times 0.06 plus 30,000 minus 10,600 squared times 0.38. I'm running out of space here, but minus parentheses, sorry, plus parentheses, it's always plus, 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 negative 10,000 minus 10,600 squared times 0.56. So there's always the squares that go inside there, and I'm just replacing the x with the x values going down the line and matching up their parentheses or their probabilities. So now I can go to my calculator and I get, oops. And I just got to remember it's going to be the square root of that. Ooh, I don't like how that looked. The square root. So, and most of the problems you're going to do are only going to have like 3 instances, okay? So parentheses, 80,000, 1, 2, 3, minus 10,600, close parentheses squared, times 0.06, plus parentheses, 30,000, 1, 2, 3, minus 10,600, close parentheses squared, times 0.38, plus parentheses, negative 10,000, 1, 2, 3, minus 10,600, close parentheses squared, times 0.56. Enter. That is not my answer. It's a big number. Second square root of that. If you want to do the square root on all together, you could do that. 25,877 and 40 cents. $25,877.40, which is a big standard deviation. So there's big swings. In other words, you can win big and you can lose. So there's a very large standard deviation. We'll talk about how we can play this game more and more times and how that affects the expected value, as well as how it affects the standard deviation once you play this game more and more. The idea here is that we can decrease the variance if we play the game more and more and more and more times. But right now we're just focusing, we're going to play this game once. What's the expected value? What's the standard deviation? That's all I have for you for today. Have a good weekend. Homework's on Google Classroom from the textbook. I'll see you on Monday.